Good morning, everybody. In last class, we were discuss about the first colligative property. First colligative property. Name of that colligative property: vapor pressure lowering. Vapor pressure lowering. Or it is also called as lowering of vapor pressure. Lowering of vapor pressure is the first colligative property. Understand? This first colligative property, vapor pressure lowering or lowering of vapor pressure. Lowering of vapor pressure. Under this first colligative property, we studied first point, vapor pressure of liquid. Vapor pressure of liquid is same. What is vapor pressure of liquid? The pressure of vapor, exerted on surface of liquid is called as vapor pressure of liquid. Suppose, for example, when a vessel containing water and it boils at 100 degrees Celsius temperature, after boiling that, some vapors occurs on the surface of liquid, that is called as vapor pressure of liquid. Means to what? Up to boiling, the vapors cannot occurs on that surface. But whenever that solution is boiled, then vapors can occur on the surface of liquid, that is called as vapor pressure of liquid. This first point is understood. After that, second point is lowering of vapor pressure or vapor pressure lowering. Vapor pressure lowering, that is delta P. According to textbook, what is the definition of vapor pressure lowering? When a non-volatile solute is added in solvent. Non-volatile solute is added in pure solvent to form the solution, and the vapor pressure of solution is lower than that of vapor pressure of pure solvent, is called as lowering of vapor pressure. That is actual definition. According to that definition, delta P is equal to P01 minus P1, where P01 is the vapor pressure of pure solvent and P1 is the vapor pressure of solution. This indicates that the vapor pressure of solvent is greater than vapor pressure of solution, is called as lowering of vapor pressure. But this definition can be defined by other way. How? The difference between vapor pressure of pure solvent and vapor pressure of solution is called as lowering of vapor pressure. But this equation is very important. Understand these equations. Delta P is equal to P01 minus P1. Then third term can also study RLVP. RLVP is a short form, but actual long form of that RLVP is the lowering of vapor pressure, relative lowering of vapor pressure. So the relative lowering of vapor pressure RLVP is equal to delta P upon P01. So depending upon this formula, we can define the ratio of lowering of vapor pressure to the vapor pressure of pure solvent is called as RLVP. This is one way definition. Other way, the lowering of vapor pressure divided by vapor pressure of pure solvent is called as RLVP. Up to this point, we studied. But note one another point is what? RLVP is equal to delta P upon P01. But delta P is to what? P01 minus P1. P01 minus P1 divided by P01. This formula can also write this way. But here one note is mentioned. What is that note? Note delta P upon P01, that is the relative lowering of vapor pressure. Relative lowering vapor pressure is equal to X2. Is equal to X2. This is very important equation. It shows that RLVP is equal to mole fraction of solute. It shows the RLVP, relative lowering vapor pressure, is equal to mole fraction of solute. Mole fraction of solute. So this equation can indicates RLVP is equal to mole fraction of solute. So first is the vapor pressure of liquid, second one is the vapor pressure lowering, third one is the RLVP. After that, next point, molar mass of solute. How can calculate? But for that purpose, first of all, see X2 is the mole fraction of solute. Likewise that X1 is the mole fraction of solvent. Mole fraction of solvent. We would require X1, X2 both whenever the numericals can be solved. So X1 is the mole fraction of solvent and X2, X2 is equal to mole fraction of solute. In any solution, when the solute is dissolved in solvent to form the solution. Is to what? X1 and X2 can mix together, then we can form the mole fraction of solution. X1 plus X2 is equal to mole fraction of solution. Mole fraction of solution. But actually mole fraction of solvent or solute, how to calculate? Which is formula for that calculating. X1 is equal to, X1 is the mole fraction of solute, that can be calculated N1 divided by N1 plus N2. What about the N1 and N2? Where N1 is the number of moles of solvent and N2 is the number of moles of solutes. Then X2 is equal to N2 divided by N1 plus N2. What it indicates? So these both components X1 and X2, both components X1 and X2 are of the solutions. The first component X1, that is solvent, its mole fraction can be calculated by using number of moles of solvent divided by number of moles of solution. This X1 and X2 can indicate number of moles of solution. Means to what? How to calculate the X1? Whenever the X1 is calculated, at that time you can take the N1, the number of moles of solvent, in numerators. On the other hand, when you can calculate the number of mole fraction of solute, at that time, at the numerator, you can take the number of moles of solute divided by number of moles of solutions. Means to what? For calculating both mole fraction of solute or solvents, we have to require in denominator total number of moles of that solution. But in numerators, we can take the number of moles of calculating components. What? Calculating components may be solvent or solutes. Whenever you can calculate the solvent, then take the N1, number of moles of solvent, and calculating for the number of moles of solute, then takes in numerator the number of moles of solute. Okay? Where N1 and N2, N1 number of moles of solvent, that can be taken as a bigger proportion in solution, solvent N1, and N2 is the number of moles of solute. Then question may be again, how to calculate the N1 and N2? We know X1 and X2 is calculated, but how to calculate N1 and N2? Which are the N1 and N2? For that purpose, N1 is equal to W1 upon M1, and N2 is equal to W2 upon M2, where W1 and W2 are the weights of solvent and solute, where W1, W2 are weights of solvent and solute. Understand? W1 weight of solvent and W2 weight of solute. Then M1, M2 are molar mass of solvent and solute. W1, W2 weights that may be taken in grams or kilograms of solvent and solutes. Again, M1 and M2 are the molar masses of solvent and solute. So for calculating X2, we have to require the N1 and N2, and for that N1 and N2 we have to require the W1 and W2. By this way we can calculate anything. So okay. So this point is very important. Delta P upon P0 is X2. That is the number of moles of solute. After this third point, RLVP, then see the next D point in vapor pressure lowering, that is molar mass of solute. Molar mass of solute from vapor pressure lowering. Next D point of this correlative property, molar mass of solute from vapor pressure lowering. Molar mass of solute from vapor pressure lowering. In board pattern, we have to ask 3 marks question. Calculate molar mass of solute from lowering of vapor pressure or vapor pressure lowering. Then, how to use the answer? So, for writing answer, we know the relation between RLVP and mole fraction of solute as follows. We give the back reference in this equation. What we know? We know the relation between RLVP, relative lowering vapor pressure, and mole fraction of solute as follows. What is the relation? Delta P upon P01 is equal to X2. Put that equation number 1. All of you know. So lowering of vapor pressure is equal to X2. Then, but for mole fraction of any components in the solution, but mole fraction of any component in solution. Mole fraction of any component in solution. Any component in the sense that will be solute or solvent. Mole fraction of any component in solution is equal to is equal to its number of moles divided by total number of moles of solution. Understand that? We know what mole fraction of any components for solid or solvents divided by total number of moles of solution. For that purpose, x2 is equal to n2 divided by n1 plus n2. x2 is equal to n2 divided by n1 plus n2, and we know that n1 and n2. n1 is the number of moles of solvent and n2 is the number of moles of solutes. Where n1 and n2 is already known. n1 is the number of moles of solvent, and number of moles of solute, Then, but for dilute solution, n1 is greater than n2. Understand this point? Dilute solution means what? The solution containing very less quantity of solute. Dilute solution means what? The solution containing very less quantity of solute is called a dilute solution. In dilute solution, therefore, n2 is negligible and n1 is too much higher. Therefore, n1 is greater than n2. n2 is greater than n2. Hence, n1 plus n2 is approximately equal to n1. n1 is greater than n2. Therefore, n1 plus n2 is approximately equal to n1. Therefore, x2 is equal to n2 divided by n1 by putting this value in above equation. Whenever putting this value in above equation, we get x2 is equal to n2 divided by n1. So, put this value in above equation. Putting this value in equation first. Which value? x2 is equal to n2 divided by n1. In equation first, delta P upon P01 is equal to n2 divided by n1. n2 divided by n1. Put this equation number second. This is the equation number second. But suppose for making the solution, we know that how to form the solution. When weight of solute is dissolved in weight of solvents. Suppose we prepare solution. Suppose we prepare solution by dissolving W2 gram of solute. How to prepare the solution? Dissolving W2 gram of solute in W1 gram of solvent. W2 gram of solute in W1 gram of solvent. The moles of solute and solvent, the number of moles of solute and solvent, the number of moles of solute and solvent are as follows. N2 is equal to W2 upon M2, we know that, and N1 is equal to W1 upon M1. Number of moles of solute and solvents are N2 is equal to W2 upon M2 and N1 is equal to W1 upon M1. Putting these values in equation second. Putting these values in equation second, we get delta P upon P01 is equal to what? In N2, what is N2? W2 upon M2 whole divided by W1 upon M1. W1 upon M1. Then say again. So we get actually what? Delta P upon P01 is equal to this W2, M2, W1, M1. W2, M2, W1, M1. So it indicates W2, M1 divided by W1, M2. W2, M1, W1, M2. By rearranging equation, we get delta P is equal to this value. But actually, we have to calculate M2. So, therefore, M2 is equal to, this M2 is equal to W2 M1 divided by W1 into delta P upon P01. So, this is the equation for calculating. Molar mass of solute by using lowering of vapor pressure. This formula is very important for the numericals. By using this formula, we can calculate the number of problems. M2 is the number of moles of, M2 is the molar mass of solute. W2 is the weight of solute. M1 is the molar mass of solvent. W1 is the weight of solvent, and delta P is the lowering of vapor pressure, and P01 is the vapor pressure of solvent. Or this formula can also write this way: M2 is equal to W2 M1 divided by W1 into P01 minus P1 divided by P01. This P01 again we can write in another way, in upper sides, or likewise that. This P01 can again put on upper sides. So this formula can also used by this way. So here molar mass of solute can be calculated. In next class we are going to discuss about some definitions. Okay, thank you.